Hi, I'm Jinwoo Kim from Gaze+, and I'll present our work, PinchCatcher, enabling multi-selection for gaze and pinch. Multi-selection is used in various computing platforms for file management, office work, programming, and even for gaming in 2D platforms. It could provide a comfortable and efficient interaction experience by providing simultaneous actions on multiple targets. But how do we perform multi-selection in XR environments? In the previous works and application, they utilized button inputs or direct touch with controllers to perform multi-selection. On the controller-free context, they utilize various hand gestures for making volumetric area for selecting multiple targets. However, in recent XR HMDs with gaze and pinch as a primary controller-free interaction technique, it is still open how multi-selection could be supported in this context. Therefore, we tried to answer this research question. How can users, while holding a semi-pinch state, add more targets to the selection by gaze without accidentally including unwanted items? We set up some design consideration based on the previous works. First, we tried to use the mechanism of previous 2D platforms to make the techniques more familiar to users. Next, we tried to embed the mode switching functions in the process of pinching actions to maintain the multi-selection interaction in one hand. Lastly, we focus on the serial way of multi-selection, where users have to group objects by subselecting each one by one, which is more general context in current XR. First, we explored how the multi-selection is activated and performed in the representative platforms. There are several methods utilized for each platform type. However, since it is hard to use persistent mode as using UI buttons or multi-selection activation in a controller-free XR environments, we chose quasi-mode for our design. This method is a mechanism of activating multi-selection mode only during the specific condition is satisfied. For instance, holding a Ctrl or Shift key for a multi-selection in desktop environment. Next, we utilize the semi-pinch action in order to make the interaction in one hand. As a result, users can perform multi-selection in semi-pinch state. The full pinch was used for final selection, and users could perform interaction as dragging in this state. Lastly, they could disable all the grouping by pausing full release pinch. Based on this standard, we designed 4 multi-selection techniques. Basically, users can start multi-selection by pausing semi-pinch and gazing the target objects. Then they confirm by performing specific action as gaze dwell, pinching, swipe, and tilt. I'll explain each in details. For the SemiNDH, users pause semi-pinch with their dominant hand, which is right hand, and gaze the target. Then they can subselect with non-dominant hand, which is left hand, pinch clicking. For SemiDwell, users uses gaze dwell for 250 milliseconds for subselection. And for SemiSwipe, users swipe their semi-pinch state dominant hand to left side until the cursor touches the target. For SemiTilt, users tilt their dominant hand right to the 30 degree to confirm multi-selection. Lastly, we designed full DH, which is a baseline technique that is inspired from the keyboard and mouse mechanism. As we press Ctrl key with our left hand and mouse click with the right hand, full DH uses non-dominant hand pinch for multi-selection mode and dominant hand pinch clicking for subselection. Next, we conducted user tests to evaluate the design techniques. We used scatter target grouping test, which participants had to group all the targets on the flat grid layout. There was 3 variations on target number per trial, 2, 4, and 6, which is often for serial multi-selection use case. It was repeated 15 times for each target number and technique combinations. For evaluation, we used these metrics: test completion time and accidental subselection during trial, error rate based on the grouping result. For fatigue evaluation, we measured hand movement and rotation. We also collected questionnaire and ranking with brief interview. With this experiment design, we recruited 30 participants from the university. We used repeated measures ANOVA on the collected data, and the results of test completion time showed only a main effects of target number, but there was no difference between techniques. This represents that the number of targets is increased, they spend more time to complete multi-selection. For the error rated metrics, there was only a significant main effects of techniques. The full DH caused more accidental subselection during trials than other techniques, and semi-swipe error was lower than the SemiDwell and SemiNDH. For the error rate, which is the end result of grouping, showed that SemiDwell and SemiTilt was significantly higher for full DH and SemiNDH, but here SemiSwipe error rate was also lower than the SemiDwell and SemiTilt. So it showed that full DH and SemiNDH caused more error during trial, but users have corrected these errors. However, SemiDwell and SemiTilt still had errors in the final group. On the other hand, SemiSwipe showed less accidental error during the trial and error rate in final group. In terms of hand movement and rotation, there was main effects for each factors and interaction effects in both metric. In common, the movement-based confirmation techniques, SemiSwipe and SemiTilt, showed the most hand movement and rotation. Also in both metrics, SemiSwipe, SemiTilt, full DH techniques showed hand movements or rotation increased more larger as the number of target increased. Lastly, in terms of system usability scale questionnaire, the free demand test showed that there was a significant difference between techniques in physical demand and performance factor. Participants rated SemiNDH technique physical demand most and SemiDwell least. For performance, the full DH, SemiNDH, and SemiSwipe was rated higher than the SemiTilt and SemiDwell. And for the ranking, SemiDwell and SemiSwipe was most preferred by participants. We summarized the results here as a key findings. Please refer to our paper for more details. Based on these findings, we propose possible applications to show how multi-selection could be used in Gaze and Pinch context. First, we propose file management scenario that users can select multiple photos for sharing, copy, delete, and drag to other locations or folders. Next, we present RTS game application that users can select their multiple space fighters with our techniques and relocate its positions based on their strategy. To wrap up, overall, we propose one-handed multi-selection interaction with semi-pinch for Gaze and Pinch context. The results show that using two hands was familiar, but it caused more errors and eventually shows similar performance using one-handed techniques. Similarly, participants prefers the semi-swipe techniques most in the user experience metrics. Using one hand also has advantage of higher task flexibility that users can manipulate the target objects with their non-dominant hand or conduct other tasks simultaneously. Next, we propose movement-based subselection confirmation method as SemiTilt and SemiSwipe. The non-movement techniques as SemiDwell had Midas touch problems. Also, pinch-based techniques as full DH and SemiNDH was too much independent from the gaze that made users hard to synchronize between gaze and pinch timing. In terms of tilt, the error rate was low, but participants felt more fatigue when using these techniques, and it was too sensitive on their movement. Therefore, it is essential to select appropriate micro-gestures for subselection, and the results show that SemiSwipe method was the most affordable way in both performance and user experience perspective. Still, there are some limitations in current study. We only focus on the serial type of multi-selection for general context in XR, but it could be extended to include parallel type in future study. Also, we evaluated our techniques in 2D UI layout, but since there are other various features in XR 3D environments, further study on exploring how it could work on 3D features is required. Lastly, there are some restrictions in variables as semi-pinch detection distance. In future approach, these variables could be personalized and be adaptive to the context. To conclude, this paper proposed a novel multi-selection function for gaze and pinch by using semi-pinch for mode switching and hand movement for subselection confirmation. Eventually, we found that semi-swipe was most preferred by participants and showed best performance. Based on the test results, we have proposed our techniques on the application for future usage. With this approach, we could keep the interaction in one-handed, and it could also enhance compatibility with the predefined interactions. Thank you for listening.